PSK. This is PSK technique only, but differential PSK. So the point to be noted is differential PSK, in short, DPSK is a non-coherent modulation technique. It doesn't mean that we don't need basis function at all at the receiver. No, we need the basis function. We are going to generate cos 2 pi FCT at the receiver, but you need not to phase synchronize this with that of the transmitter. So no phase synchronization is required. Okay, if phase synchronization is required for this basis function with respect to transmitter, what will you do? How do we establish phase synchronization in regular in practical cases? Very simple. We use one complex circuit, okay, as I said, so which will track the phase of the incoming signal on the channel. So by using the incoming signal of the receiver, we track the phase of that signal using some complex circuits, right? But in some of the applications, what they do, they transmit carrier signal along with the transmitted signal. Okay. Usually, what we do, we send only one signal called by name transmitted signal, which is modulated signal. But in certain applications, along with this modulated signal, one pure carrier is transmitted on different channel. So we use two channels for transmission. On the first channel, we use the transmitted signal, S(t), that goes to the receiver. Parallelly, on another channel, we send C(t), the carrier signal. So two signals are coming to the receiver. In the receiver, we take that carrier as the basis function for the receiver, and we do the coherent detection. Okay. But what the problem here is, we are wasting one channel for this one, because bandwidth is very useful resource, right? We cannot afford bandwidth many of the time. That's why this is not a good advice for all the cases. This is a good advice for the cases where the channel is in abundance, available in abundance, but it's not a good advice always. Okay. If you want to track the phase information from the incoming signal without using another channel, that time you need complex circuits of the receiver. Right. But in DPSK, the modulation technique what I'm going to discuss today, we don't need to establish phase synchronization between transmitter and receiver. Okay, right. That's why it's called non-coherent modulation technique. Right. So I've given the bullet points on the screen available. It is non-coherent modulation technique, no synchronization. Here I'm talking about synchronization means phase synchronization, right? No phase synchronization needed between transmitter and receiver. Okay. So in DPSK, we perform two basic operations. First one is differential encoding. Second one is PSK. So this shows that it is PSK itself, phase shift keying itself. But before we do PSK operation, we have to do something called differential encoding. Then you have to go for PSK, right? And some of you may get doubt something like that. Name itself is PSK, phase shift keying, where phase is most important. Then how do you say it's non-coherent, no phase shift required? Means no phase synchronization required between the carrier of the transmitter and carrier of the receiver. Otherwise, during modulation, we need the phase. Okay, leave that discussion, not required at this point of time. Okay. Look into the block diagram next. So as usual, the first part is input binary sequence, which is denoted as BK, which is a sequence of ones and zeros, which is given to one logic circuit or logic network. This logic circuit is your digital circuit. Okay, maybe consisting of some gates, right? Basic gates. This logic circuit will perform an operation on the incoming binary sequence. This operation is called differential encoding. It's an encoding. Encoding is a process of arranging incoming ones and zeros in a particular fashion, right? Encoding is a process of arranging ones and zeros, the input binary bits in a particular fashion according to your requirement. Then the output of the logic circuit is taken as decay. This decay is also sequence of ones and zeros. Okay, only they have rearranged in some fashion. Okay, in what fashion these are rearranged? Okay, that equation I have given at the bottom of the slide. Look at this differential encoding. It's here. Differential encoding dk is equal to vk xr dk minus 1 bar. Right. Can anyone of you identify what operation it is in digital logics?
XNOR.
XNOR, right? No. So you identify that one, right? Oh, strings, na? Okay. The screen visible now?
Oh, sir.
Yeah. Okay. Guys, this is XNOR operation. Okay. Why I've chosen XNOR operation, we'll discuss later. It can also be XR operation. So it is XR or XNOR. Anything is okay, it doesn't matter, right now. So you have to do some operation like this.
The screen is not visible.
Which one? Screen is not visible? Huh?
Screen share ಮಾಡಿ sir.
Okay, share ಆಗೋದು ಹೋಗಿತ್ತಾ? One second. Okay now?
Yes, sir.
Okay. Come back. Okay. The last equation, what I have given is XNOR operation. And you can also do XR in place of XNOR. It doesn't make any difference, right? The differential encoding, what I am calling here, is just simple XR or XNOR, or even you can say modulo 2 operation, mod 2 operation. That operation is performed on incoming binary sequence, right? To get another sequence, which is called DK. So BK is converted to DK. BK is converted to DK. This particular is information converted to DK. Both are binary sequence only, ones and zeros only, right? Right. After that one, this DK is connected to delay. Delay is a circuit which introduces a delay of TB, that is 1 bit duration, TB, one symbol duration. After that, it's given back to logic circuit. Okay, look at this, guys. Okay, remove this. Can you see here the DK minus 1? This is DK. Fine. This part is DK. This is DK minus 1. So the sequence DK, after applying to delay, it becomes DK minus 1. So 1 bit delayed. What does it mean? The sequence DK, which is available now, is stored in delay. After storing a delay, it will be delivered to next symbol, coming next symbol after TB seconds, right? So at the logic circuits, we have the two inputs. One is this flow, BK. Another one is DK minus 1. That is this portion and this portion, right? These two are the two inputs. One is BK, another one is DK minus 1. So this logic circuit will perform XNOR operation, this one, and BK and DK minus 1 to produce the output as DK. Okay, that is a simple logic circuit you can easily understand. Before I go to next part of this slide, let us go in detail. What happens inside this logic circuit? Why we have to do like this? After doing, what happens? Okay, so for that, you have to go to next slide. Look at this operation, guys. This is your XNOR operation, truth table. 0, 0 is 1, 0, 1 is 0, 1, 0 is 0, 1, 1 is 1. So if you summarize this table, it appears to me in a different way. What is that one? Here. Okay. If you look at this dk minus 1, which is 0, here also dk minus 1 is 0. So in two cases, dk minus 1 is 0. Okay. When dk minus 1 is 0, what happened to your bk? So when bk is 0, dk is 1. Did you observe this one carefully? Similarly, in the third case, when bk is 1, dk is 0. So what do you conclude from this one? dk minus 1 is 0 in both the cases. Forget it. So we go to the condition of dk minus 1, which is 0. If dk minus 1 is 0, what happens to your bk? If bk is 0, dk is 1. If bk is 1, dk is 0. Right. So inside the logic circuit, the input is inverted and produced as output. I'll come to some conclusion. What is this one? When dk minus 1 is 0, the input bk is inverted and it is produced as dk. Okay. Look at the other combination. If dk minus 1 is 1, here also. So there are two cases. When dk minus 1 is bk 0, dk also 0, bk 1, dk also 1. Right. So this property of XNOR is used here. It's used here. So that one is given here as a summary equation. So when dk minus 1 is 0, dk equal to bk bar. That is inversion. When dk minus 1 is equal to 1, dk equal to bk. That input output remain same. Right. So keep this concept. This is what is XNOR for us. Right. Okay. So that's what happens in our differential encoding. Okay. So using this property, I explained one example here. Okay. First thing, understand this bk part. So assume bk a sequence, something like 1 0 0 1 0 0 1 1. Any sequence is okay. Right. Now from bk we have to prepare dk. You have to prepare dk. Right. So for that we need dk minus 1. In the very first of bk, dk minus 1 is not there because unless bk comes, dk minus 1 won't come. You recall our block diagram here. The input is bk. Fine. The input is bk. To get this dk minus 1, we need to have dk first. Dk is not yet produced. So in the initial condition, dk minus 1 is not available. Okay. That's why to start with the operation here, what we do, look at this. I have given one bit here, which is called by name reference bit. Reference bit. The reference bit. It is assumed, okay? It is assumed either as 1 or as 0. In this case, I have assumed that reference bit is 1. That is dk minus 1 is 1. Even I have shown the same bit here, dk minus 1. The same thing is here. So both are same. I have shown the arrow. You can clearly see that. So this one bit is taken as dk minus 1. Next, bk is also there available. This bit and this bit. Oh, sorry. This one and this one. Okay. So what is that combination? This first combination, 1 1. Tell me, When it is 1, 1, what is the output in your XNOR operation?
dk equal to vk.
Yeah, according to the table, 1, 1, dk is also equal to 1. That is shown here, 1, 1. Okay, so you can see this full combination 1, 1, 1. Visible? Likewise. So 1, 1, 1. Come back here. Here I gave 1. This is also 1. And output is also 1. This operation is over. Fine. Input is 1. Delay is also 1. Then is 1. Next. Come to second data. In this case, your second bit is 0. When the second bit is 0, what is your dk minus 1? 1. Where this 1 come from? This 1 come from previous dk. The previous dk, after giving it to delay, it becomes dk minus 1. This comes over here. And finally, these two will be XNORed now. Okay. After XNORing 0 and 1, you will get 0. Like this, the complete sequence dk is prepared. Hope you understood. Right? So, bk is the incoming sequence. dk minus 1 is extracted from output. Output is fed back to input through the help of delay. So two sequences are available, bk and dk minus 1. So both after XNORing will give you dk. Okay. Go to next slide. Right. So finally, dk is here. dk is here. Now tell me, what is the difference between bk and dk? Guys, this dk depends upon the input, present input bk and the previous input dk minus 1. Right. So dk is not only depends on the bk, but also depends on the previous output, that is dk minus 1. So through this operation of XNOR, I'm trying to bring in the dependency of output dk on the input bk. Right. If delay element was not there, then present to dk was depending upon present bk. That means present output was depending upon present input. But because this XNOR operation, present output depends on present input and previous output. Okay. So through this XNOR operation, I am making one dependency of the present output on the previous output. Present output on the previous output as well as the input. Okay. That means the present output, I can't use the table. The present output, what is called dk. Sorry. The present output dk depends upon bk and dk minus 1. So I'm differentiating between bk and dk minus 1 to produce the dk. Hence the name differential encoding. Right. In this case, I'm finding out what is that one? Whether both the inputs are same. Both the inputs are not same. That's all. So differential encoding, in summary, will just check whether both the inputs are equal or not equal. So that is a differentiate between bk and dk minus 1 to produce the dk. That is called differential encoding. Okay. This logic circuit was not there. If logic circuit was not there, then the dependency on input and output would not have been there. Okay. So I'm intentionally creating dependency. So that means present bit depends upon previous output bit, so that it produces another output called dk. Okay. This information is very useful in receiver to get back our information, right? Next, we go to the next block, amplitude level and network. So look at this one. Amplitude level network is a part of BPSK. This BPSK modulator is exactly same as the modulator, what I have discussed in earlier class. Okay. Test two parts, amplitude level network and product modulator. We know that one. In BPSK modulator, the input sequence should be converted to NRZ polar form. NRZ polar. That means it should have root EB, comma, minus root EB combination. For bit 1, amplitude level must be root EB. For bit 0, amplitude level must be minus root EB to perform PSK. So that's why we use amplitude level network. So that input 1, 0 combination becomes root EB, comma, minus root EB combination here after raising the amplitude levels. Then it is given to product modulator. Product modulator multiplies your input amplitude root EB or minus root EB with the cos 2 pi of CT with appropriate equation. Finally, it gives a signal called S of t. Okay. If you look at the block diagram, what is visible on the screen, it is complete BPSK modulator. No change in that one. Okay. After adding this extra block of logic network, the output becomes DPSK, differential PSK, right? Okay. If I ask you what is DPSK, so how it is different from PSK, it's simple. DPSK is same as your PSK, except this extra logical operation called differential encoding. That means before doing modulation, the input sequence has to be encoded properly, right? That's what this. Okay. The block diagram is explained here in another way, right? Okay. First one, we take the BK, then we generate DK minus 1. After that, we will get to DK. So the sequence is available. So this sequence of DK is applied to next block. So in the previous slide, we have seen after logic circuits, what are the next block? Amplitude level encoder, right? So this amplitude level encoder performs an operation on input sequence 1 and 0 and convert the amplitudes of 1 to root EB, 0 to minus root EB. The same thing is shown here as polarity, okay? When there is a bit 1, we make it plus root EB. When there is bit 0, we make it minus root EB. So keeping that in mind, I have written here plus minus plus minus. So plus stands for plus root EB, minus stands for minus root EB. So this is the output of the amplitude level encoder in the transmitter, right? After amplitude level encoder, what is the next block? Product modulator. What product modulator does? It multiplies the output of the amplitude level encoder with the basis function, the carrier signal, that is root of 2 by TB, that is root of 2 by TB, cos 2 by f. Okay, now the last block, PM, product modulator. This multiplies this cos function with the root EB and NR. So if root EB is multiplied with this basis function, then what happens? You will get root of 2 EB by TB, cos 2 by f. If it is multiplied with minus root of EB, then amplitude will be minus root of TB. That means the output of the product modulator is having the equation, that carrier signal, with either positive amplitude or negative amplitude. Okay. So the output of the product modulator is either having positive amplitude or negative amplitude. Okay. If it is positive amplitude, we assume that it is the regular carrier. If it is negative amplitude, then we say that it is introduced 180-degree phase shift. So the output of the product modulator is having two phase shifts, either 0-degree or 180-degree. With positive root EB, we introduce 0-degree. With negative amplitude, we use minus root EB. Okay. So this is what the idea. So keeping this in mind, I have shown here, okay, the phase of transmitted signal. Read that one. Phase of transmitted signal. That is output of the DPSK. What are the phase? What are the phase? Whenever there is bit 1 here, the phase is 0. That means carrier signal remains same. Whenever there is 0, the phase is pi. Pi means 180. That means amplitude is minus. Okay, that's how it is written. Whenever there is 1 1 1 1 at dk, we have written 0 0 0 0 phase. 0 0 0 phase means it is not the bit 0, it is the phase 0. Right. So whenever there is a dk equal to 0, we have showed a phase shift of 180 degree in the form of pi. Okay, this is what is happening. Okay, so after this phase is obtained, the waveform is shown here. Look at the waveform. For 0 here, for 0 phase, the carrier signal is remaining same. Instead of cos wave, I have taken sine wave just for convenience of ease to write. Okay, now don't bother about that. So since it is here 2 zeros, 0 and 0, I have written 2 cycles of sine wave, again 2 cycles of sine wave. These sine waves are in regular pattern. That is, there is no phase shift there. Okay. Whenever pi comes, that is 180 degree phase shift. 180 degree means inverted. I have shown here inverted sine wave there. Okay. Inverted sine wave is shown here. So that makes it one period. Again 2 zeros. Again 2 zeros here. The 2 zeros are shown here. Same thing. The waveform. Okay. So how this waveform is written now according to you? Very simple. This waveform is written based on this phase. This phase comes based on this amplitude value. Okay. Now look at this one. If you carefully observe here, the decay. Whenever there is 1 1, I have written the sine wave as it is. Whenever there is 0, I have written the sine wave inverted sine. Here also. Okay. That means it is just PSK operation. PSK operation on decay, not on BK. BK is the input. BK is encoded, then converted to DK. After DK, it is PSK. Okay. In exam, you'll be asked to write DPSK waveforms. Very simple. Take the input sequence, what is given, do the XNOR operation, convert it to DK. After getting DK, write the waveforms of PSK waveform, keeping DK as the first sequence. That's it. That's how to write the DPSK waveform here. Okay. So after converting VK to DK, just what I told so far. Is put it on the slide once again here. Observe carefully. Go to this part, first part. When this dk minus 1 is 1, okay, dk minus 1, where this dk minus 1 comes from? There is a reference bit, because my first bit is this fellow, bk. You start with this one, enhance. Okay. My first bit of information is bit 1. And this dk minus 1, this fellow, is assumed. We have assumed that one. Okay, it is there. So this dk minus 1 and this one, both put together will give you dk. And dk sequence I have given. Right. Now I want to compare the output of the transmitter with respect to bk, the input sequence. Right. This 0, forget about this one. Okay. This 0 comes after performing, right? After performing the encoding operation. Fine. Wait. How this operation is done? Recall what I explained so far. This initial bit is combined with this fellow. Differential encoding is done. Between these two, differential encoding is done. So 1 XNOR 1 is 1. Next 1 XNOR 0 is 0. Next 0 XNOR 0 is 1. That's how it is done. Okay, now I've given only BK and DK. I've skipped DK minus 1, it is there. Your DK should be shifted and assumed yourself, right? So after getting DK, the complete thing, I've written the phase of the DPSK signal, phase of the DPSK signal. Whenever there is 0 phase, 0 phase, 0, 180 phase, 0 phase, 0, 180 phase. That's how this phase is written, right? Now look at the differentiation you have created. That means differential dependency you have created, correct? Differential. Assume that at the receiver, you are getting one waveform whose phase is 0. First waveform coming to receiver is a cos function, that is a carrier signal with 0 phase. That means cos 2 pi of ct is coming to you, right? Now you observe for one more waveform, next waveform, that is also 0. So two waveforms are coming to one after the other. Both of them are 0 and 0. What this 0 and 0 indicate? Right. Both of them are no phase shifts. Correct. Both of them are. First signal, that is this fellow, is available for a period of 0 to TB. Second one is available for TB to 2 TB. That means to explain you some concept, I have taken two successive symbols, one from 0 to TB, another one TB to 2 TB. Okay, now these two I'm observing at the receiver, right? Both of them are 0, 0. When the two waveforms coming consecutively to the receiver are 0, 0, what was the bit transmitted? Bit 1. Bit 1. Keeping it in mind, guys. When the two waveforms coming in the same phase, 0, 0 phase, contain bit 1 information. Next one. Next two symbols you take. First one is coming with 0 phase. Its next fellow coming with 180-degree phase shift. That time the information sent was 0. That means your phase are opposite. One is 0, another one is pi. That time your information bit was 0. Go to next combination, third combination here. 180-degree first signal coming with, the next following fellow coming with no phase shift of 0. That time information bit was 0. Did you observe this combination? Next when you go here, both the incoming signals consecutively having the same phase. That time the information bit was 1. So if you observe this relation between the phase shift and the input sequence, you will come to some conclusion, right? So what is that conclusion? If the two waveforms coming one after the other, that means one waveform you take for one period of TB, another waveform you take for next to 1 TB. So if you observe carefully the two waveforms over 2 TB period, over 2 TB period, if the phase are same, that means 0, 0 or pi, pi. Both of them are having pi and pi phase, 180, 180, or both of them are 0, 0. That time your message must be bit 1. Or if the two signals coming with the 0 phase and 180 phase, that means if you observe for 2 TB, two waveforms, both of them are inverted with respect to each other. One fellow 0 phase, another fellow pi phase. The time the information bit was 0. This is the effect of differential encoding. Effect of differential encoding. Okay, effect of differential encoding. What is differential encoding? Recall, when the information bit is 1, when the information bit is 1, then the carrier is, when the information bit is 1, then the output is no change. No change. That is 0, 0, 1, 1, 1, 1. So both are same. If it is 0, that time it's going to be 0 pattern. So if you go back to the table and observe carefully, it happens. Got the idea? So that waveform, so I have explained here also. Look at this one. Okay. This portion. Here. So if you observe for 1 TB, observe for another TB, both the waveforms are same. If you come across this waveforms in the receiver, I declare the bit is 1. Otherwise, here sine wave is inverted. Here also inverted. So minus amplitude. So waveforms comes like this: minus amplitude, or plus amplitude. That time we declare that send bit is 1. On the contrary, here positive amplitude, here negative amplitude. That means a positive amplitude signal is followed by negative amplitude, or negative amplitude signal followed by positive amplitude. The time your bit is taken as 0. So this is the concept we adapt at the receiver to recover information back. So in my receiver, I don't want any phase synchronization now, right? I need not to develop a carrier with phase synchronization. You need a carrier, but not with a phase synchronization. So the complex circuit part is not required for us. What you have to do observe second waveform with respect to first waveform. Second waveform, first waveform. Second one, first one. Second one, first one. So if you observe this one, we'll get 4 combinations. So what are the 4 combinations? Both plus plus or both minus minus. In this case, symbol was 1. Otherwise, 1 plus 1 minus or 1 minus 1 plus. In this case, symbol was 0. So in DPSK, you need to observe the waveforms, received waveforms for a period of 2 dB, not for 1 dB, 2 dB. That means the present waveform should be compared with previous waveform. You have to see them. Both of them are same or not. Same, bit 1, not same, bit 0. This is how to decode at the receiver. That's how the receiver should work